So, welcome to pattern analysis. If we have a quick look at our schedule, we are now in the middle of these somewhat confusing weeks that we always have in the summer term, because in turns there are these like free Thursdays, and then there is the week with the Bergkirchweih, where the Monday and Tuesday are off, and then the week thereafter again Thursday is off, which always creates a bit of a mess. So Thursday last week was off. Okay, we probably everyone realized this. Today we meet and we can talk a bit about sampling and have a closer look at this paper by Rasmussen. This Thursday will also be a meeting, but it will catch up on the clustering topics that we haven't really discussed yet on Thursdays. And then in the week thereafter, the Monday will be a public holiday. The Tuesday is usually without lectures. So we will meet on Thursday, like as an exception to the usual rule, let's say. Yeah. And I'm going to talk about variational inference there. I swap topics. Okay, I can explain this later. We will talk about approximate inference. So in 10 days from now, we will meet again. And then there's the 7th week where again the Thursday is a public holiday. So we will talk about dimensionality reduction. We will meet on Monday. And then in the week, like starting from the week of 8th, everything will be a bit more regular. With one exception, I'm out of town on June 8th. So we swapped also the program there. But we will come to this. Okay. But now let's see that we safely navigate more or less through these weeks where we have these holidays, the public holidays, and try to keep track of things. So the overall topic that we're concerned with is to say, okay, yes, we have these Bayesian models. We talked about clustering. There were some, let's say, ad hoc-ish approaches, we could say, the k-means and the mean shift. Not entirely ad hoc-ish. I mean, there were equations involved. But in terms of the theoretical framework, the deepest is the Gaussian mixture model. Because when we start to look into the question, how many components could we assign for a Gaussian mixture model, how many components are a good fit for the given data, then it turns out that we can essentially follow this Bayesian trail and say, well, okay, the number of components is kind of a hyper, some form of a variable, an additional variable that needs to be endowed with a hyper prior, and so on and so on. So it becomes more complex, and it turns out that we need additional tools to solve this. And this is where we are stuck right now. So one possibility to do this is to go in the direction of sampling and say, okay, we formulate this GMM fitting as an inference task in a large probabilistic model. And this inference task, we cannot solve it analytically, but we can approximate it with a Markov chain Monte Carlo method. This is one way how it can be done. This is what we're going to discuss this week. There are also other opportunities. and this is what we're going to talk about next week, will be variational inference as an alternative to this. So the idea of variational inference is then to say, well, okay, can't we just define the task in a different way, like with functions that we actually can solve? So we make a little bit of an approximation error by taking a simplified functional form, but then on top of that, we don't need to do any further approximations. We can just solve it. So that's the variational inference path. And like both have their advantages, the sampling path and the variational inference path both have their justification, have their advantages. We will talk about them. And yeah, I think that's also the reason why, if you ever look at Bishop's book, these chapters are just next to each other. No? So two ways of trying to solve the same kind of problem. Okay, so for today, sampling it is. For today, we had the slides, we have the paper, and I prepared 3 essentially slim questions. The third one is can get a bit extensive though, but the first 2 questions are essentially little follow-up questions just to make sure that we all are on the same page. Sorry. Okay. Sampling as approximation to inference. The lecture provides an example for sampling-based inference, the calculation of the expectation of a random variable. We also touched here in this meeting the topic of Bayesian linear regression. So the same type of sampling-based inference can be performed there. Let's talk about this, summarize in your own words the idea and key steps, plural, of this way of performing inference. Task number 2, applications and limitations of rejection sampling. We will come to this. And task number 3 is to look at the paper by Rasmussen. We will do this together, of course. Before we start with these points, do you want me to follow up on something in particular from the lecture, to like discuss something or to repeat something? Okay, so yeah. Yeah. The standard linear regression estimates a vector, I forgot how we wrote it, either with beta or with W, a weight vector that multiplied with some input gives you a prediction, no? Something along these lines, yeah? Gives a prediction y, a scalar prediction. And in Bayesian linear regression, these weights are not just parameters, but these weights are distributions. If you want to keep it simple, you can say these all are little Gaussian distributions. So effectively, 2 parameters suffice to describe each of these distributions. So you can say you have, instead of a weight W1 or so, you have a mean value mu1, and you have a standard deviation sigma 1. And for weight 2, the same thing. So if you say, okay, to me this also looks like parameters, and then if you count, you can say the number of parameters doubles, no? But the nature of the calculation also changes a bit, because if this is not one value, but instead a little Gaussian around some mean, mu1, with some standard deviation sigma 1, then it means the outcome of the multiplication is also a distribution. So you're multiplying the x, essentially, like whatever you have here, you multiply this with a distribution. And at the end of the day, if you say, okay, like the standard linear regression gives me one curve, yeah? So let's say this gives you one curve, something like this. You fit it to your training data, of course, no? Let the axis be the training data. What you get out of the Bayesian linear regression is a distribution of curves as a result. And this is a bit surprising at first, but let's take the same training data. So you have, so these are the observations during training. Now let's say we would have the same mean curve maybe, yeah? So let this be the mean of our distribution of curves. But now, depending on where we are here, we have different standard deviations. So at the locations where we actually made observations, maybe the standard deviation is very small because we actually have evidence, oh, here's an observation, so it should really be this value up to some measurement inaccuracies, noise, and so on. That could also model, but okay. But at locations where there are no observations, so between these two observations, for example, standard deviation would be expected to go up. So the family of curves is then something, if this is the mean, and this would be something like the equivalent to a standard deviation or so, just indicated, no? So then you have something like a belly of curves here. Okay, this is not a super nice distribution here to simulate, but that's the idea. Oh, and here, like there's no observation anymore in that direction. So probably it totally spreads, because if you think about each of these little functions that you're fitting as being one polynomial, then you can think, okay, if like certainly the polynomial is constrained from these four observations, yeah, but depending on what this polynomial actually is, yeah, it might totally fizzle out here in the part where we don't have any observations anymore. No? It's like if you're fitting a quadratic function and you look at the outset, then already small changes in that fit can have dramatic changes. No? And we're seeing something similar here on the outside. Yeah? So what we get is a distribution. So the solution is a distribution of functions, which you can say, I don't care, and just take the mean, then you're effectively falling back to the standard linear regression. But you could, for example, say, hold on, I mean, the distribution also carries a little bit of information. No? For example, you could say, apparently, if my standard deviation is very low, then apparently I'm quite close to one of my observed values. So I can maybe use this as a proxy for confidence. I can say, okay, So in that neighborhood, I actually made observations. So probably it's a more reliable prediction as opposed to some area where the standard deviation is quite large, which I could use as an indicator that actually my model gives very unreliable predictions in this part. No? Could be one possible, like tangible benefit, no? of the linear regression. Now, we didn't go through the whole thing, but I think I kind of sketched at least something similar early on in the semester. I don't know, maybe in the second meeting or so. If you double check the videos, you'll find it. Yeah. So, but we don't need to know the whole math. No? Essentially, we need to know what we get. So instead of fitting a single function, we are fitting a distribution of functions. This is the result of the Bayesian linear regression. Okay. Now let's get back to how is the expectation evaluated? Oops, sorry. I need to type my password. Oh yeah, okay. Better. So what if we want to calculate the expectation of a function f? How can this be done? Okay, what is the expectation? I mean, how is it defined? What is an expected value? Okay, yeah, it's like, I didn't fully understand it, but you take the function value and you take the probability of having that input, no? Yeah. So effectively it means like we're feeding a random input to a function, no? And we are interested what comes out on average when feeding that random value. The problem with random values is that they have some distribution. No? It's not automatically a uniform distribution. So that distribution has to be taken into account. No? So we can say, okay, so here's our random value, p of x. No? And that value we are feeding to that function. Sorry, am I messing this up? Anyways, this value I'm feeding to a function f, and we repeat this experiment very often, so we do it over the whole domain, like we draw all values that we can possibly draw, and then due to the p of x, like values that are more likely will show up more often in our evaluation. No? And then we check what is the outcome of that experiment, and this is the expected value. No? So this is what on average one would obtain. No? And it's super important in machine learning because very often we're learning these averages. It turns out we're learning, like the training objectives usually boil down to learning some average, so with respect to something. Okay. Now, one thing that was already very not so nice when we talked about the inversion sampling was that we need it's always super inconvenient if we need to have this distribution P of X if we need it explicitly represented somehow. Yeah, this is always a recipe for trouble. No? It's expensive and so on. So if your expectation calculation is part of some inner loop of some bigger process, then you don't want, just as one step of calculating the expectation, you don't want to be in that stupid situation that, oh, now I need to somehow interpolate my whole density P of X in order to be able to evaluate this product. Yeah? Okay. And this is where the sampling comes in. No? So the idea is to say, look, I mean, this is nice, and this is certainly super accurate, but it's also too complicated. All I'm doing is I'm sampling something like 10 values from this distribution P of X. And then I'm feeding these 10 values to that function f, and I take the average of those. Yeah? It's perfect. Good approximation of the expectation. And this is actually very commonly done. Yeah? If you think about training of deep neural networks or so, this is a standard routine. Yeah? Okay. We can discuss a little bit like what. So it works well. Nothing bad to say about this. But maybe what is neglected if we say we're sampling? So instead of creating this P of X, we draw 10 values from P of X and average. Take the average outcome as an approximation for the expectation. What might get lost there? I mean, 10 is a small number. No? So, yeah. So the 10 values represent this density, the density of X. Yeah? So we are lacking a bit the application, or we haven't really talked about like what is that expectation? Is it an expectation in a casino? Yeah, we gamble, no? and we want to get an expectation, or what is it? No? Is it, but these 10 draws, they give a representation of this density. No? So what might get lost? I don't know. We can have different densities. Can look at different densities. These densities are always just simplified world views. Okay, who did something like a computer vision class or a deep learning class or so? No? Then imagine this being like the LION data set, no? You're training on images from the internet, for example. Hmm? What happens? Yeah. The random variable, I mean, it depends. you can say it's continuous, you can say it's discrete, it doesn't matter. If you say it's discrete, I would, yeah, it doesn't really make a difference necessarily, no? What might, I don't know, but, yeah. I can't hear you. Yeah, I mean it is a coarse approximation for a distribution, no? I mean, because in particular 10 values. I mean, what are these 10 values? No? These are I don't know. Let's say, okay, these are not 10, but let's pretend these were 10. Or let's say we draw only 5. Okay, these are 5. No? And then the question is, which of these distributions was it? No? It's not so immediately obvious. No? You can say, okay, here's a bit of a higher density. Maybe this one. No? That could also explain this one out here. No? If this is a Gaussian or so, it has these like infinitely long tails. But it could also be a different one, actually, to be honest. No? Because like having 3 close to each other, this could literally also be a uniform distribution. No? And okay, so with 10, maybe it would be a bit clearer. Or let's say we are generous, we do 20. No? With 20, it gets a bit clearer. But then by tendency, if we would have a distribution with, let's say, a denser region and long tails, then it's very likely that a lot of our samples will be in this denser region. And what is underrepresented, these are these rare events, no, that are out there, no? The long tails. This is something that is just hard to capture, or maybe impossible to capture if you say, I'm relying on 10 draws or 20 draws to represent, to sample here from this big distribution. No? So it's a bit, so even though the expectation itself might be good, no? If you're interested in questions beyond only am I getting a good expectation value here? If you're wondering, is the underlying distribution well represented, then you have to say, well, it depends. No? If there are long tails, maybe I never see them if I'm drawing these 10 values. No? Okay. I'm just saying this as a general remark. No? Yeah. Mm-hmm. Okay. So, but other than that, it's perfect. No? We do 10 draws from P of x, and we get a good estimation for the expectation. No? And the exact same thing you can do for the Bayesian linear regression. No? You can say, wonderful. No? If each of your weights is a Gaussian distribution, I do it the exact same thing. I make 10 draws of these weight vectors. So let's say weight vector 1 is my draw number 1. Then weight vector 2 is my second draw, and so on, until I have my 10 draws. This means I literally get 10 polynomials out of this. So I can draw them, and from these 10 polynomials, I can also calculate, if I look at the intersection here, with the x-axis, I can literally, from these 10 functions going through this, I can calculate the standard deviation here. It's not a problem. Yeah? So it is like having a distribution of functions, but approximated through these 10 draws from the possible like infinitely many like distributions that we would be having here. No? Okay. And then we can say, well, this is these 10 draws, they form our solution, like the resulting distribution. So this is the way of getting the posterior distribution or some approximation of the posterior distribution. Hmm? Does that make sense? I'm trying to illustrate this Bayesian. Bayesian stuff is always confusing, I would say. But at the end of the day, I hope you see that like you can cook it down to something that is quite mechanical. No? Like a posterior distribution is not something like magical or so. No? It's something that you can say, okay. If I roll the dice 10 times here for these weights, then here's my family of functions. Okay. Yeah, just a quick. This is more or less just reproducing things about the rejection sampling, or an alternative of this was adaptive rejection sampling to go for the log of the distribution. So let's briefly talk about the constraints, because I think they are a bit subtle or they are a bit tricky. What constraints have to be satisfied to enable or permit the use of rejection sampling? In what cases can it bring an advantage over inversion sampling? In what cases is it just not a good choice? How does it work? How does rejection sampling work? So again, we start with a distribution somewhere. So what's the idea of rejection sampling? Yeah. Okay, Gaussian. Okay, good. Okay, yeah, good. All right, so there's this, let's say, more complicated distribution. We say, okay, this is too complicated. Let's take a simpler distribution from which we can sample. So let's say a Gaussian distribution, yeah? For example. We draw a random number from that, because by design, this is a distribution where we can do it. So we end up here. And then we know, okay, if we evaluate the Gaussian at this location, it's here. So let's also evaluate the density here. So P of x is this value here. So we say, okay, on that whole range, let's draw a uniformly distributed random number. And if it's within this range here, we keep it. So x is the value that we want. If it's outside, we reject it. No? That was the idea. What would be the difference? So a Gaussian, we can say we choose a Gaussian because it's simple to draw a number from a Gaussian. You know, what is simpler? A uniform distribution. Why not choose a uniform distribution? I mean, we could. It's not forbidden, honestly. It's not forbidden to take a uniform distribution here and say, okay, this is the first one from which I draw a number, just a uniform number. Maybe I draw this, I don't know. And then I evaluate P of x here. I find out it's here. And then I do the same thing again. I draw my uniformly distributed number there. Check, is it in this range? If yes, keep. Otherwise, reject. What do you think? Or we could also, I mean, now we have uniform and Gaussian as a candidate. We could also say, what about, we said, from exponential distributions very broadly, we can also analytically sample. Would also be a choice, no? To take an exponential distribution instead. What distribution would be a good, or why choose one over the other? So. Yeah. Oh, because of the domain? Okay, you do have to make an assumption that the domain here is bounded somehow. Yeah, okay. So this is something that you have to make. Otherwise, yeah, I mean, okay. Yeah, so for the uniform, you need some form of bound. No, but the choice of the function impacts the number of rejections or the risk of rejection that you're incurring. No? So it depends a bit on what you know about your underlying distribution. No? If you believe that a Gaussian is an appropriate approximation, appropriate upper bound, then go for a Gaussian. No? If you think a uniform distribution is an appropriate upper bound, go for a uniform distribution. And the rejection risk is essentially this integral here. This is your risk of rejection. No? And the larger this area is that is above your actual density, the more likely it is that you have to repeat the whole process and repeat and repeat. Like the larger, and this is a bit of a, I mean, this can be a bit of an annoyance, of course, no? If you have only very coarse information about your distribution, no? Or if it's a very high-dimensional, if it's a high-dimensional vector here, we will see this when we talk about dimensionality reduction, then also this rejection area here, by definition, will always be very large, even if we seemingly have a nice fit. But the higher the dimensions, the more difficult it is to be really tight on that function. No? Okay, so this is a limitation. But of course, there can be cases where you say, okay, I do have some prior knowledge. No? Think about, for example, physical problems. No? You have light coming from a certain direction, and then some interaction with a photon might happen, no? Like a scattering. No? And then you don't know in advance, like in which direction it will scatter or with which exact angle, but you do have a model for that. No? So you can say, okay, there's something like a probability distribution that I can say, okay, no? And in order to approximate that distribution, I can fit a Gaussian on top of that. And then I'm absolutely in the game, no? Because I have a good model for the overall shape of that distribution. No? You could say, yeah, okay, I have a physics textbook here. So I just take that scattering, these scattering equations. And why should I do this intermediate step of doing the rejection sampling if I already know, actually I'm not sure that it's a Gaussian distribution, but let's pretend it would be. Yeah? If I already know that it's a Gaussian distribution, why wouldn't I directly sample from that Gaussian distribution? Yeah? And then you could say, yes, if in a situation where literally this one interaction with the object is the only thing you have to observe, then it would be better to sample from that Gaussian directly. Yeah? But maybe there are other obstacles in the path. Yeah? So for example, you have light coming in, then you have your object that scatters, and then maybe you know that there are two further objects out there. You don't know exactly where or how and so on, no? But they could induce some secondary effects down the road. And yes, overall you might have that Gaussian, but you have also a little bit of a disturbance in that Gaussian due to these other like impurities, you could say, of your experiment. No? And then it's a very useful method. Because then you can still say, oh, okay, look, I know the overall shape is a Gaussian. I know things can be a bit distorted here, so maybe the likelihood, the probability is at some locations here, I have a bit more probability mass than expected, at other places a bit less. So let's take a Gaussian multiplied by some safety margin, 1.1, 1.2 or so, that nicely envelopes this space. No? And then everything is fine. It's a nice sampling method in that case. No? Okay. Yeah, so this is one big assumption, is that you can get a good envelope function. Let me write this down. So a good envelope function. So good meaning like with a small red area here. So one that tightly fits. And the second assumption is that you need to be able to evaluate P of x. Yeah? So this can be then your like actual detector readout. No? For example, our physics department was involved in an experiment where they were looking for neutrinos in an ice cube, like in an Arctic like sensor array, like a large sensor array. No? And then the question is like, did something arrive here? Or did something arrive there? So then you can say, okay, I will check and see what my actual count is at this and that sensor node, for example. No? Okay. what can be an advantage over inversion sampling? So the one that we discussed very early on in the lecture. Do you recall this method? It was this idea to say, oh, if I have a probability density function, then I can calculate the CDF. And then based on the slope of the CDF, I can draw a uniformly distributed number along the y-axis, see where it intersects, and this is my draw from the distribution here. But what can be an advantage of the rejection sampling over the inversion sampling? Depends a bit on the assumptions, no? So these assumptions apparently can be cheaper than whatever assumptions we need here. What assumptions do we need here? Yes, you need to be able to calculate the CDF, which means that you need some representation of the full density. No? So requires the CDF. So usually this means this implies that the whole density P of x is required. And this is, this can be a problem. And here we only need to evaluate it at the very location where we drew a number from our envelope function. Yeah? And this only at, let's say, 10 locations if we do the same 10 times estimation game or so. No? So in that sense, it can be much easier than the inversion sampling. Okay. Let's have a look at the GMM fitting paper. What do you think? Not sure whether you had the opportunity to look at it. The title is, the infinite Gaussian mixture model. Infinite in the sense that we can add components or we can remove components, so we don't have a upper or lower limit or so in the number of components. It's a bit of an older paper, but it's easy to see. But I think it has its benefits in the sense that it's relatively stripped down to the essentials. On the other hand, it also has its disadvantages. It's quite dense at some points and might require a clarification here or there. But of course, one of our goals is also to sort of learn to read. So let's try it. Okay. Let's have a quick look at the abstract. In a Bayesian mixture model, it is not necessary a priori to limit the number of components to be finite. In this paper, an infinite Gaussian mixture model is presented, which neatly sidesteps the difficult problem of finding the right number of mixture components. Inference in the model is done using an efficient parameter-free Markov chain that relies entirely on Gibbs sampling. Okay. So before we go into the details, a bit of a high-level view on the paper. So, okay, introduction by today's standards, super short. Then we have an introduction of what they call, or what the author calls a hierarchical mixture model. I think in the sense of a hidden variable model, the way how we studied it. Math, 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 math. Okay, then here in section 3, an extension to like an arbitrary number of components is how I would translate the infinite limit. And then experiments in section 4. Yeah, in section 4 are the experiments. Section 5 are the conclusions. And that's it. A couple of references. That's it. Okay. It is a Bayesian model very much like what was shown in the slides. Let's look at this first, maybe just to recall what's going on here. So I hope you remember this picture here. So, okay, now we can fully see it. No, I'm sorry. Ah, yeah, here we are. So, this is a Gaussian mixture model with the observations here xi. These are actual observations. This is why it's a shaded node. Yeah? And there are I think we called it responsibilities the first time that we talked about the expectation maximization fitting and so on. So here these hidden variables set I indicate it belongs to component 1 or it belongs to component 2 and so on and so on. Yeah? Okay, so this is a hidden variable. And every observation supposedly belongs or has been created from, in a generative view, to one of the components. So we have this plate here with these, where we say, okay, if we have n observations, we also have n of these responsibilities associated that each of these observations belongs to one of the components. Yeah? Okay, so this is the core here. And then there are these k components. They are further specified here in this block. So each of these components is a Gaussian. So it means it has a mean, which is also something hidden. So it's not a shaded variable. It's a mean and a standard deviation or covariance if we go higher dimensional. And these and k of these. No? Okay. And so the means and the standard deviations, they are, if it's a fully Bayesian model, they also need priors. So the thinking is, okay, each of these components has to be created from some, like it cannot occur at arbitrary locations in the space, but there's some area where they can occur. And this is what the priors indicate. So there's some area where they can occur for the mean vectors. This is important. And what their shape is. These are the priors for the standard deviations or the covariances. Yeah? And these are here in Wikipedia location, there's like there's like a prior mean. You could say this is the center of your coordinate system or something like this, no? And some contraction or wideness parameter lambda, no? And also the covariances are guided by two of these hyperpriors here, nu and sigma 0 square. Okay, so this is one part of the model. And the other part of the model is to describe the possibilities for these responsibilities a bit more. Because it turns out in a Gaussian mixture model, you have these weighting terms pi. No? Let me write this down really quickly. So P of x is the sum of a number of Gaussians weighted, or let's use it k equals 1 to k. So component number k is weighted by a weighting term pi. Yeah? And you could say, okay, so maybe I have one large component, no? Where 30% of the data is explained by that component, and then I have a couple of smaller components that each maybe take 10% of the remaining data. So I have a total of 8 components then. Yeah, or 7, 8, yeah. So this distribution about like what are the component magnitudes, this is governed here in this single vector, you could say, for the components. And this also has a prior which is denoted as beta here. It will be denoted as alpha in our paper. No? Okay, so this is the full model. No? So we have these components specified. We have these prior weights specified, and we have the link between the observations and the components specified here with these responsibilities. And none of those can somehow occur at totally arbitrary locations. They all have some priors, so there's a bit of an prior information where we are in the space and what like possible distributions are. Okay, so this is the overall setup. Now I would look a little bit more into the mathematical details that are shown in that paper. So essentially they use the same model. It's just that they use a bit different notation. Yeah, okay. In equation 1, notation is still very much in sync. We have the weights. So this is a Gaussian mixture model in that notation. So let's look at the right-hand side first. We have the weight for a Gaussian, and we have the Gaussian here, which is essentially what we have written here. And each of these Gaussians is described by a mean, and here is the inverse of a standard deviation, so it's a precision. Yeah? Okay, but you can change this, like whichever you find more useful. Okay, we have k. So components have the indices j. Okay, I can change this. J equals 1 to k. Okay. And the observations here are not called x, but they are called y. Okay. And the author makes the dependence of these observations, so makes the generative model explicit by writing all these parameters here. So we make the observations y, given that they are supposedly generated by means, standard deviations, component weights of our Gaussian mixture model. Yeah? So this is the way how this is to be understood. Okay. What I don't like too much in this paper, but here it's not easy to find when you quickly skim through it, but in this paragraph, another type of variables are snuck in. And these are the indicator variables, what was set on the Wikipedia page, like which component is responsible for which observation. So these are the values CI, one for each observation here in this paper. And this is how we can then go into the details. We don't need to we don't need to do all the calculations now. It would also be a bit painful. but let's try to understand the structure of this whole thing. Yeah? So first part, component parameters. The component means mu j are given Gaussian priors. Okay, so what does that mean? So we have a space here. So if this is our space, we say, well, eventually we will have a clustering here with different components. Yeah? And we say all these means, they get one prior from which they are drawn, and this shall be a Gaussian prior, which is maybe centered here, I don't know, yeah, and has maybe a wide standard deviation, essentially indicating in the absence of data, this is where priors mostly matter. Yeah? If we don't really have observations that tell us otherwise, why don't you put your means somewhere in the domain of this Gaussian here? Yeah? And then based on that, we can draw mean number 1, mean number 2, mean number 3. So that's the meaning of the component means mu j are given Gaussian priors. So all means originate, like if we think about it in terms of priors, originate from a Gaussian with mean lambda, which is a hyperprior, or it's writing hyperparameter here, and a precision R, which holds for all the Gaussian components. And then the lambda and the R, this goes a bit beyond our Wikipedia model. They themselves also become, obtain a normal distribution and a gamma distribution as priors. Okay. Where, and here's an interesting thing, mu y and sigma y are the mean and the variance of the observations. Footnote number 1. What is that footnote? Strictly speaking, the priors ought not to depend on the observations. The current procedure is equivalent to normalizing the observations and using unit priors. A wide variety of reasonable priors will lead to similar results. This is a very common excuse, I would say, in Bayesian modeling. So they say, okay, like these are the priors of the priors. So we just check our observations, what value range do they have. We align it with that value range, but these priors of priors, they don't matter a lot anymore. No? Okay. The shape parameter of the gamma prior is set to unity, corresponding to a very broad, vague distribution. Okay. So, and now they say the conditional posterior distributions for the means are obtained by multiplying the likelihood from equation 1, conditioned on the indicators, by the prior in equation 2. So So this is our likelihood, but it shall be conditioned. So this is the part that I don't like on this indicator that has been snuck in that paragraph, and multiply it with the prior that we have for the mean. And then we get, because they are conjugate, what we get out is again a normal distribution, the probability for these means, given indicators, observations, precision, and the hyper parameters gives that normal distribution here, where y bar is some, let's say, average value of samples that we are responsible for. It's literally like a responsibility. Okay. Yeah, and then it goes on like this. So similar argument, it's like multiplying the likelihood and multiplying the priors is what in this whole section we keep doing. For the hyperparameters, equation 2 plays the role of the likelihood, which together with the priors from equation 4 give conditional posteriors of standard form. Standard form, what he wants to say is an equation for which we have a closed form sampling procedure. So the closed form sampler will be what helps getting this Gibbs sampling procedure iterate. So okay, so yeah, so he's forming a Gaussian here, another gamma distribution, and these are all, without looking at the specifics in here, these are all distributions from which analytic sampling methods are known. And he's continuing like this. Let me skim a bit fast forward, just and skip some of the equations, because an interesting remark is here after equation number 9. So we're talking about what was beta? We would have to look it up. But now we're coming to a distribution that is not of standard form. So it's a distribution for which we don't have an analytic sampler. But now we come into the situation that it can be shown that the log distribution of beta is log concave. So we may generate independent samples from the distribution for log beta using adaptive rejection sampling. So this is where this argument comes in. Sorry. That we say, okay, we do have an equation there where we can provide a very nice envelope. Now the envelope not for the rejection sampling, but for adaptive rejection sampling in log domain. But we don't care, it's the same principle. Yeah? So we can provide a very nice envelope. So we have the benefit here that we have an efficient sampling technique, despite the fact that it's not like an analytic sampler for this is not known. Yeah? Okay. Okay, then let me briefly bring to your attention that for the mixture weights, the pi's, they are using a so-called Dirichlet distribution. Is maybe not one of these distributions that are commonly subject in machine learning lectures, but it's just for a discrete distribution. It's oftentimes used as a prior. So why discrete distribution? Because if we have k components, then each of these components has a certain probability pi, like pi 1, pi 2, and so on. So we can say if we need a prior for a discrete distribution of that type, then the Dirichlet distribution is like a beta distribution just for the multivariate case. Okay. So they are defining a Dirichlet distribution, and things go on, go on, go on. And now let's have, so after equation 15, we essentially have a Gaussian mixture model where all variables are expressed in this form of conditional distributions. Yeah? So whatever it is, the indicator variables, our mixture weights, and so on, for everything exist conditional distributions. So it means once we worked through section 2, we could write down a Gibbs sampler already. Yeah? The Gibbs sampler itself is not complicated anymore. So essentially, it consists of a loop where we say, okay, as a first element, we update our first, was it mu or whatever the first one was in that list? Yeah. So let's first sample a new mu1 drawn from that Gaussian, no? Sorry, we need to use equation number 4. This is the posterior. So anyways, still we sample mu1 drawn from a Gaussian because these are conjugate priors. Yeah? Then mu2 from that Gaussian, the same Gaussian, just with different values plugged in for the second component. No? So we need responsibilities for the second component, and so on. So for all k means, so all k variables mu j, this is done. Then you can draw from the the posteriors of the precision must be somewhere hidden here. Here we have the posteriors for the mixture weights, and we have the posteriors for the responsibilities. So we can, like in so and so many sampling steps, we can update all these variables here and the responsibilities that are part of the model. Yeah? So this is one long loop to update all these model parameters, and you let it run, let it run, let it run. This is a true sampling step. So it means also unlikely solutions can be chosen. That's fine. Yeah? It's not a maximum likelihood, so where you go for the maximum. No? It's a true sampling step, and you iterate. Okay. So it's not hard to implement if you manage to implement these sampling procedures. No? Okay. And now in section 3, the extension is how can we get flexibility with respect to the number of components. So this is this infinite limit here. And the argument that he's making here, I think is not so easy to, not 100% easy to understand, or I find it quite involved. It builds on top of the equations in section number 2, But let me just tell you the result. So the idea is this. Several ideas come into play. One idea is that he says, okay, if the number of components can now change, so effectively in one of these iterations, or during this iteration, I have to update the component number, and this is closely linked to the responsibilities. No? So let me just merge this together, and responsibilities. So which sample has been created by which component, likely. Yeah. So let's think these two steps together. Yeah? And let's just say, so we can clarify in a second how it works, but let's just say we have a mechanism that assigns every sample to a component. Yeah? What we can do is we can go through all samples and can check what is your component number, for example, what is your component number, what is your component number, and we can make a list. So we can make a list of components that have samples and forget components that don't have any samples. Yeah? So this would mean that we are shrinking if there are a number of candidate components and to one or two components no sample is assigned, we just remove it from our data structure and leave it out. Yeah? So that's one idea. And this mechanism is built into the calculation of the responsibilities. So for the responsibilities is there's a mechanism that says sample from the components your new membership. And this includes a special option. So you can take one of the K components that are already out there, but you also have a special option. You can choose component K plus 1. This includes the possibility to choose component K plus 1. So this doesn't exist. Yeah? So this doesn't exist yet. But we can say in the next iteration, then we have one component more. Yeah? So the whole flexibility about the number of components is built into this step. Yeah? It can be the case that when responsibilities are newly assigned, that a new component is created, or it can happen that if we're checking the list of used components, that it turns out, oh, this component is not used anymore, apparently, and then it can be dropped. So this brings us to the question, how does this sample from the new components, your new membership thingy, how does that work? And which of these equations is it? I think it's that one. let me just write it differently because the notation is so terrible. Okay. So it's somewhere between equation 16 and 19. And the idea is this. So if we look at this specific aspect, so the idea is this, that we have two factors that influence the likelihood of component membership. So one is how large is component J. So larger components are apparently more important or more attractive or whatever. So then this should give a bonus. And then times where is component J. Yeah? So these are the two things that come into play. So let me express this as an equation. So how large is component J? This is what we see in equation 16. So number points assigned to J. So this is in equation 16, upper row, n minus ij. So we take I out of the assignments and check how many other points are assigned to J, divided by the total number of points, total number of points, minus 1 plus this Dirichlet distribution, like a width parameter, you could say, no? Like a diversity parameter, you could say, no? Alpha. Let me not explain it too much here. So this is about like the relative number of points assigned to it. And where is component J? Well, let's look at the Gaussian. No? We have a Gaussian in our Gaussian mixture model. So this is something like the pi, we could say. And the Gaussian here, we can directly take it. So we can check this, this current observation y I. How well is it explained by component number J with respect to its mean and its standard deviation or covariance? There's also an extension to multivariate case. Yeah? So this is location, and this is magnitude or attractivity or so of that cluster. Yeah? And this you can evaluate for every J, like for every cluster, you can say, this cluster is there, it's so and so large, and so and so close. No? That cluster is over there, so and so large, so and so close. So you get a list of value, like J different values for these J clusters. And then, so this is a distribution from which you could sample. But you need one additional value for the possibility that actually you want to create a new component. And this bonus component or extra component has a special weighting term, and this is what we need this alpha for. So it's the second row in equation 16, alpha divided by n minus 1 plus alpha. So this is the missing probability mass, you could say, the diversity parameter that helps create new clusters, times, yeah, and here we also have a normal distribution that is somehow drawn from all of our hyperparameters. Let me try to read this. It's this wild integral here. Over all these components here somehow. I don't know. I didn't study it properly, but let's say some hyper-Gaussian that we have here, no? And this is the alternative. So you always have k plus 1 choices, and you can say sample from this. Yeah. So this is the magic mechanism, or so you could say, to increase the number of clusters or to reduce the number of clusters. And since it's part of that iteration, there's a certain interplay between the fitting and this evolution of the clusters. No? So new clusters can emerge, new clusters can also vanish again, it can shrink. No? And the clusters that we have in the next iteration, they will be updated by all these equations that we looked at, yeah? Like sampling from all these values. Okay. So so on one hand, it's terribly complex, yeah? But on the other hand, it's actually also somehow simple in a way, no? If you're not forced to write down all these equations, no? Of course. So then it's a relatively simple computational procedure, but it's not cheap. You need a lot of iterations. This is what we saw then from the experiments. I think I have this picture in the slides, no? So they let it run for a couple of thousand iterations. So one iteration is one run through this while loop here, yeah? And as you can see here on the y-axis is the number of components. The number of components, it is not so that it settles to, oh, it's 18 or oh, it's 20 or so, but it changes underways, no? And whenever you stop, this is essentially the solution that you have, like drawn from the space of all Gaussian mixtures, no? Zack, here's your solution, no? And here's a histogram that just, yeah, here's a histogram of the components. So apparently there is a preference for 18 to 20 components here, but depending on where you look, no, it could also be 20, 21, 22 or less. No? It's also a possibility. Okay, yeah, maybe I just stop here. Do you have questions? All that. We can also come back to it at some later point in time, of course. But I hope you find it interesting because it's kind of special in a way, I would say. Even though, of course, I mean, the math is a bit involved if you go by it like symbol by symbol. It's quite a bit to calculate, of course. No? Okay, but I wouldn't expect you to do that, of course. Okay, then, yeah, thank you and see you then. No?